Так, рабочий стол. Теперь вы должны еще и видеть мой стол.
Да, видим стол.
Всё.
Больше.
Отлично, отлично. Ну да, теперь вы можете прям на первое. Тут сегодня первые парты точно будут свободны.
А у меня будет работать еще долгое время.
Что еще раз?
Я говорю, она будет свободна еще долгое время.
Ну да, да. Так. Так-то можно уже и начинать, да, по сути. Так, мне остается только сначала здесь посмотреть, выровнять, как мы будем видеть с вами все. Так, я пока так переключусь.
А пока похвастаться, у нас тут интернет мобильный 100 мегабайт.
А это у вас там 5G, что ли, поддерживает? Или вы близко к станции?
4G, LTE плюс Advanced у нас. У меня не поддерживает 5G телефон.
Да, ну теоретически эта симка может и 5G.
Да, но как-то так.
Супер, супер. Здравствуйте.
Да, безлимитный. Но стоит дорого.
Ну, там, наверное, дороже, да, относительно наших цен. У нас в стране относительно демократичные цены по тому, ну, по ресурсам и по цене, так скажем. По опыту в Германии уже знаю. Ну, 100 мегабайт это, ну, конечно, по воздуху.
В Германии дорого был?
Да, в Германии там больше покупают именно трафик. Там покупается трафик на месяц. Поэтому мы больше пользовались Wi-Fi точками в этом плане. Ладно. Здесь у нас видно. Тут смотрим. Единственное, что нужно сделать вот так, наверное. И заранее приготовим слайды. So.
Спасибо
Welcome.
вам
Да.
тут будем мешать.
Спокойной вам ночи. Отдыхайте, восстанавливайтесь.
Ну, спасибо. Думаю, со следующей недели мы уже будем онлайн смотреть, когда будем в отеле в Китае.
Хорошо, ну, если будут вопросы, можете там либо через ребят передавать, либо письменно как-то там, не знаю, по почте писать, в принципе.
Ну, к примеру, допустим, если нам будет что-то понятно там в течение лекции, если мы посмотрим запись, мы в начало новый придем, вот так, как я сейчас, к примеру, спросим что-то, и, к примеру, уйдем.
Да, хороший вариант, да.
Хорошо, хорошо, спасибо.
Все,
До свидания.
до свидания. So, welcome in today's Aasp lecture. So, in previous lecture, we finished with these least square solutions, and I think we will start with special smoothing here. So, first thing, special smoothing is one type of preprocessing step which give us the extension of the time snapshots, and also we can decorrelate our impinging wavefronts. And here you can see that in this case, Also, we have one disadvantage, which is we have smaller array aperture because we divide our overall number of elements into L overlapping subarrays instead of 2 subarrays. And here you can see how we choose these selection matrices. Then we change how we choose our, or how we create our measurement metrics. You can see that we concatenate measurement matrix times first selection matrix, then second, then third, etc., up to capital L selection matrix. And here I gave you one example in which we have overall 7 elements, and we want to create 4 overlapping subarrays. And here you can see how we choose these elements, and here you can see what we'll have instead of measurement matrix. And we can start our lecture with this example, where we have one connection to our today's lecture, where we say that we can use forward backward averaging. So here you can see from this example, we found with this example how many sensors we need to have for D wavefronts, which is coherent, and in case when we use maximum overlap, uniform linear array, and unitary Aasp, of course, with special smoothing and with forward backward averaging. And here you can see that, for example, if we have D coherent wavefronts, we need overall 6 elements. And if we, for example, assume that we have 5 coherent wavefronts, in this case, we need to increase the number of elements up to 8. And now let's start our today's lecture. And the main point for today's lecture is forward backward averaging, which is second pre-processing step. So this one, lecture 21. Lecture 21. So 2022, November. 15 or 16? 15th. And here we have subsection 4.4, forward backward averaging, FBA. 4.4, forward backward averaging, FBA. And of course, if you have any questions, you can ask me. So it is better to use voice because I don't see the chat. So 4.4 with background red color. And for the name of this subsection, I will use 3 black underlines. And then we can start everything. Можете садиться ближе, больше никого не будет. Большинство онлайн. So, forward, backward averaging is pre-processing step. Pre-processing step for central symmetric arrays. So it is new thing for us here. Central symmetric arrays to virtually double the number of available snapshots, double the number of available snapshots n, available snapshots, capital N, and to decorrelate the impinging wavefronts without reducing the array aperture. Without reducing the array aperture. So I will highlight pre-processing step with blue box here, as before when we have this special smoothing case. So pre-processing step with blue box. Хорошо, хорошо. And the main idea here, or main advantage, that we double the number of available snapshots n. Then, so from this main information about forward backward averaging, what we can see if we compare it with special smoothing. So special smoothing extend the number of snapshots, and this one also extended, but with this double thing. Then first one and second one, they both decorrelate the impinging wavefronts, but special smoothing. In this case, we reduce the array aperture, but for forward-backward averaging, we can save our array aperture in this case. So, but in this case, we need to have central symmetric arrays. You can see central symmetric arrays. And next, we will go for the definition, what we mean inside of this sentence. But first, let's add here that we assume identical but of course we can assume arbitrary radiation characteristics here. Arbitrary radiation characteristics. Characteristics. And for simplicity, we will use omnidirectional antennas here. But of course, we can use so maybe I will show you in my lectures. It will be easier. So we assume this omnidirectional characteristics, but also we can assume some arbitrary characteristics when we have the shape like this one. So let's write this point here. Here, omnidirectional omnidirectional antennas for notational simplicity. No, antennas for notational simplicity. And the next step is definition. So definition, two black underlines here. Centrosymmetric array. Centrosymmetric array is equivalent to the array element locations are symmetric with respect to the centroid. So element locations are symmetric with respect to the centroid. So here I will highlight centrosymmetric array with yellow color. And then to see this definition, we will use one small scratch here. So let's assume the antenna array with 6 elements. element 1, 2, 3, 4, 5, and 6. This is our antenna array. And here I will indicate it with red cross here and also with yellow color. So I will highlight it. This is our centroid of antenna array. So you can see we have 3 elements from, let's say, right side and from left side. And here we have the centroid of our antenna array. And now, no, it is, yes, the center. Because here we assume only 6 elements. If we, for example, if we have odd number of elements, for example, 7, in this case, if I'm not mistaken, the centroid will be element number 4. And as in this case, we'll have 3 elements from right side, 3 elements from left side, but centroid in element number 4. So next, I will let me show the centroid one more time here with horizontal line. And next, we will show one of the impinging wavefronts. For this one, I will use green color. So our impinging wavefront green color, and here we will use e to the power of j times mu special frequency sub I to show that this one mu sub I. So it is only one of the impinging wavefronts. And let's show what we'll have in this case. So if impinging wavefront goes like this one, so first sensor which receive this wavefront will be this one, so top one, and the last, the bottom one. So let's show that we receive this wavefront in this way. Which means first we receive here, then second element, third, fourth, fifth, and the last one, sixth. So, and this way we will call it as forward wavefront. And our idea here to virtually add the backward impinging wavefront. In this case, we represent, I will represent it with blue color. So let me show you what we'll have here. this one, I think. And for this one, I will use just pencil, like blue color. So this signal is equal to e to the power of minus j times mu I. So you can see all elements here are the same, but we have minus in the power. We will call this signal as virtual wavefront. Virtual wavefront. Or when we add minus in the power of e, so it is just complex conjugate. So this one is the mirror image. We can say that this one is mirror image. And now let's see what we will have for virtual wavefront. This one, our array, first element of our array will be this one, so the bottom part, which receive our signal, then number 5, 4, up to number 1. So let's show that in this case, let's say receive direction will go from bottom to the top. From the bottom to the top. And now, first element is the bottom element, because first we will receive, if we look to this signal as wavefront, so we will receive here, and second, third, fourth, and etc. So 1, 2, 3, 4, 5, and 6. And let me one more time indicate that here we have a centroid. So I will use red color. Centroid. And also I will add a yellow background color here. So centroid, this one, this cross, red cross with yellow background color. And now let's show what we will have for measurement vectors for our real signal or forward component and for our virtual signal or backward component. So here, for original signal, we will use vector x with superscript f, so it is forward, which depends on t, and this one is equal to the original signal, so x of t. I add here green underline to show the connection, because this one and this one are connected. Original signal, original signal. And for virtual signal, we will use x superscript b, which is denoted as backward component. So here we will use Let me check. Exchange matrix. У Скачкова уже он забрал. We'll use exchange matrix, which is denoted as P. Matrix P. This one. We use exchange matrix, and backward component will be equal to this exchange matrix P of size M times complex conjugate of original signal. So X complex conjugate of T. And for this one, blue underline. And of course, for this one, we can show that what we'll have for capital M, so the number of array elements. Here, for this example, capital M is equal to 6. And then I will give you array steering matrix of a backward array, which is equal to the same exchange matrix P of size M times array steering matrix, but with complex conjugate sign, or in the same way, it is equal to original array steering matrix times matrix delta. So I will put this equation into the box and use yellow color for highlighting. And here, what we have for delta. This equation for some unitary diagonal matrix, some unitary diagonal matrix delta, which is complex of size small d times small d. So the number of impinging wavefronts or sources. This equation is array steering matrix. Array steering matrix for the backward array, or of, let's see, of the backward array. And one more thing for this matrix delta. This matrix delta depends on the location of the phase reference. On the location of the phase reference. Of the phase reference. And you can see that we add unity diagonal matrix. In this case, if we assume the inverse of this diagonal matrix, it will be equal to the complex conjugate of this matrix. And now, so you can see matrix delta depends on the location of phase reference, but let's choose that our phase reference is located in this centroid. What we'll have in this case? Let's write down if the array centroid, if the array centroid is chosen as the phase reference. Is chosen as the phase reference. As the phase reference. So, array centroid as the phase reference. In this case, we will write antenna steering array as matrix A, but with subscript C, which means that our antenna array is centrosymmetric. Then it is equal to our original antenna array A times this matrix delta squared, or square root of this delta matrix. In this case, the square root of this delta matrix is the square root of the elements in on the main diagonal, because we have diagonal matrix. And let's see what we'll have for array steering matrix of the backward array. In this case, we multiply with this exchange matrix our antenna array matrix A subscript C, and of course with complex conjugate sign. Then what we'll have here, this exchange matrix. Here we have matrix A times matrix delta square root, complex conjugate sign. Then if we use this property, we will have matrix P of size M times A complex conjugate, when this thing is multiplied by delta inverse and square root. And here, let me show you with brown color this part. This one is equal to A times delta. You can see. So we can replace this part with A times delta. A times delta times inverse and square root of delta, matrix delta. And let me show also this one with brown color. So it is only for property of a central symmetric array. So this one, property of the central symmetric array. And then you can see, if I multiply diagonal matrix with its inverse and square root, it will be just equal to, so here, A and times delta square root. So this thing is equal to the same central symmetric array steering matrix. Then we can show that if we write array steering matrix of a backward array, which is equal to this exchange matrix times original array steering matrix with complex conjugate, it will be equal to the same antenna array matrix. So I will put this equation into the box. And we have a special name for this type of matrices when we multiply it with exchange matrix and also take this complex conjugate and we have the same matrix. We call these matrices as left P real. So this array matrix is left P real. Left P real. So why left? Because we multiply it with this matrix P from the left side. Next, here we have an example. With one slide, number 20. Example, here we use uniform linear array. For uniform linear array, we have slide number 20. So example with two underlines, also for slides here. Now first, let's switch to this slide number 20, and then we will write down array steering matrices. So we have this uniform linear array like this one, with this spacing delta between elements, and the overall number of elements is equal to capital M. And you can see what we have for array measurements here, how we can represent our measurement vector. And now the main interesting part for us here, this antenna array, let's say array steering matrix, yes, matrix A. Let's first show what we'll have if we put reference sensor at sensor number 1. So phase reference, phase reference at.
Не видим.
Yes, of course. Thank you. Let's continue. So phase reference at sensor 1. What we'll have here? We show this equation before, I think. Lecture number 17. This one. Omnidirectional sensors, phase reference at first sensor, and you can see we write down this matrix A, and you can see that we introduce this vector with fonts. And let's show this thing one more time here. So for uniform linear array, we will have array steering vector or array steering matrix as this one. So I will write down here ULA. It is equal to row vector of ones, and of course this matrix is row matrix. So row matrix of ones, then row vector of ones, row vector of ones times matrix phi, then the same row vector, but this phi matrix in the power of 2, and the last row will be equal to row of ones times phi in the power of capital M minus 1. And all these things are row vectors here. This one is row, this one is row, row, and row. So inside of this vector, we have ones. And here, I think the number of ones is equal to d. So it is real of size d. Then matrix phi is diagonal matrix with elements in on the main diagonal equal to e to the power of j times mu I special frequencies, where I goes from 1 up to the number of sources, small d. And we can show what we have for this matrix phi if we take complex conjugate of this matrix. We will have inverse of this matrix. Now let's write down array steering matrix of the backward array for this case with phase reference at central 1. We need to multiply this original matrix with exchange matrix from the left side, and also we need to take complex conjugate of this matrix. Something like this one. And what we will have here? So when we multiply exchange matrix, when we multiply matrix with exchange matrix from the left side, we need to inverse the position of rows. In this case, first we choose the row, the last row. So it is, and of course we need to take the complex conjugate of this row. So when we take the complex conjugate of vector of ones, it is just the same vector. But when we calculate the complex conjugate of this matrix phi, we can change it with inversing. So we can multiply here with matrix phi in the power of minus, and here inside m minus 1. So I will show it like this one. And let's go to the beginning of this matrix. What we'll have here? Vector of ones times matrix phi in the power of minus 2. Then vector of ones times phi in the power of minus 1, so inverse. And the last one, vector of ones. As before, we have the same row structure matrix. So this one row, row, and a row vector. And can you see the connection between these two matrices? I will give you one hint here. So if you remember, when we write like this one, we can also write it as A times some matrix delta. So first I will show here that we have this matrix A sub ULA. But what we'll have here for delta matrix? Look to the elements here. So can you see it? For example, you can compare first element here and first element here, and the last element here, and the last element here. So with which matrix we need to multiply this ULA to get this type of a matrix? No? Okay, so I will give you this delta matrix, but then we will look why we have this type of matrix. This delta will be equal to matrix phi in the power of minus m minus 1. So you can see when we multiply a row of ones with this one, we have a right thing. Then, for example, if we go to this one, when we multiply it with this one, we will have only the row of ones. And this thing, for this example, is delta ULA. So you can see that it is some unitary diagonal matrix. But now let's go to the next example when we assume that our phase reference is at the array centroid. So phase reference at array centroid. So we already have all these equations, and I will show you. Of course, we use uniform linear array. Let me move my page. Centrosymmetric array steering matrix is equal to this AULA times this delta ULA and the square root of this thing. Or we already know what we have for this delta ULA. In this case, we can show that this array steering matrix is equal to original AULA times not original, of course, with phase reference at centroid. With or let me check. No. This one and this one is equal. And next we will see what we have for a centroid. AULA, and we need to multiply it with matrix phi in the power of minus. Here we have m minus 1 over 2. And now let's show. I think I will use a lot of space here. Maybe like this one. So first element, we need to multiply this row of ones with phi in the power of minus m minus 1 over 2. So we will have row of ones times matrix phi in the power of minus m minus 1 divided by 2. Then second element is this row of ones times matrix phi, and we need to multiply it with phi. So we can show it as 2 divided by 2, this in the power of 1. And here, inside, we will have minus m minus 3 divided by 2. Up to the center of this erasing matrix, which is just this row of ones. And let's go to the last elements here. So the same row of ones, but now we have phi so we can say that this element before will be m minus 2, and we need to multiply this thing with minus m minus 1 divided by 2. We will have m minus 3 divided by 2. So as this one, the second one, but without minus sign. And the last element as the first element, but also without minus sign. So in the power of m minus 1 over 2. And we have here row, and also here. So this one for center symmetric, or let's say, yes, center symmetric array with phase reference at centroid. And this one just for center symmetric, but for phase reference at sensor 1. And one more time, this matrix is left by real. Now let's go to forward, backward, averaged special correlation matrix. So it is only the beginning, what we have for antenna. For array seeding matrices, and now what we have as the signals or as special correlation matrices. Let's write forward, backward, averaged special correlation matrix. Forward, backward, averaged, special correlation matrix. Special correlation matrix. So let me check. For this one, 2 underlines here. In previous lectures, we use special correlation matrix as matrix RXX. So RXX. And for forward backward average, we will use the same RXX, but with superscript FB. So forward backward. Next, let's write one more time what we have for forward array. So x subscript f of t is equal to x of t with green color here. And for the backward part, x superscript b of t is equal to the exchange matrix of size m times complex conjugate of x of t. So this thing with blue color. So let's start first with forward special correlation matrix. Forward special correlation matrix. Special correlation matrix. So this one we know from the previous lectures. So matrix RXX simply equal to the expected value of the multiplication here of vector x with its Hermitian. So x of t Hermitian. And you know that this thing is equal to array string matrix times special correlation matrix of the sources times a Hermitian and plus our noise. So sigma n squared times identity matrix of size m. I will put this equation into a box and also this thing into a box, and I will highlight special correlation matrix of the source elements with RSS. I will use it next when we will compare what we have if we use only, let's say, original Aasp, and what if we use forward-backward averaging. Then let's write down backward special correlation matrix. Backward special correlation matrix. In this case, instead of x t times x Hermitian of t, we need to use this exchange matrix times complex conjugate of t, and all this part with Hermitian. So this thing is equal to the expected value. Let's start with just x superscript b of t. So x superscript b of t times the same vector but with Hermitian. And what we will have here. So first we can move exchange matrices outside of this expected value operation. So we'll have exchange matrix of size m, then expected value. Inside of this thing, first we have x complex conjugate of t, and then we need to take the Hermitian of this x conjugate. So it will be just x transpose, because we have double complex conjugate, and times the same exchange matrix, because it is just the second diagonal with ones. If we take the Hermitian of it, it is just the same matrix, original one. Of course, we can show here, let's maybe that this one is equal to x complex conjugate Hermitian of t, like this one. That's why we have here transpose. And this thing, if we use our forward special correlation matrix, this one will be equal to Rxx complex conjugate. And now we can show how we average special correlation matrix using forward part and backward part. So our overall special correlation matrix Rxx superscript FB is equal to averaging these two parts. So if we have two parts and we want to average it, we need to sum it up and divide it by 2. So 1/2, and then we multiply it with, first here we have Rxx plus exchange matrix times Rxx complex conjugate times exchange matrix. So let's put these intermediate results into a box. And now let's go inside of this RxX complex conjugate. So the matrix RxX complex conjugate is equal, and we need to take the complex conjugate of this part of this array first, of this equation, this first equation. So we'll have matrix A complex conjugate times RSS complex conjugate, then A Hermitian complex conjugate. So I will leave it with both operations. So first complex conjugate and then Hermitian, plus, so the variance of the noise still the same, sigma n squared. And if we take the complex conjugate of identity matrix, we'll have the same identity matrix. And now, to move for the next step, we can use the previous equations. So here you can see that we already have a complex conjugate. So we can multiply both sides from the left side with exchange matrix. And we will have that this matrix A complex conjugate will be equal to exchange matrix times A times delta. So let's show it here. This part is equal to exchange matrix times original array steering matrix times this matrix delta. And in the same way here, so we need to take the Hermitian of this matrix multiplication. So first we start from right side. It is the Hermitian of matrix delta, then Hermitian of matrix A, and the same exchange matrix P of size m. And now let's look what if we multiply this RxX complex conjugate with these changes inside of it. If we multiply from both sides with exchange matrices, what we'll have in this case. Exchange matrix of size m times RxX complex conjugate times exchange matrix. In this case, we will have, so exchange matrix multiplied with exchange matrix, it is identity matrix. So first we will write matrix A, then matrix delta, then RSS complex conjugate, then delta Hermitian, then A Hermitian, and then we one more time multiply exchange matrix by exchange matrix, so it is just identity matrix, and then plus the variance of the noise, and here we multiply from both sides with exchange matrix B is identity matrix. So P of size M, identity matrix of size M, and one more time P of size M, and of course this thing is equal to identity matrix of size M. Now we can write what we have for forward, backward, average spatial correlation matrix. So the final result using this equation. And then we will do our break between lectures. So argx subscript FB is equal. So first, A times. So here we have 1/2. Inside of this thing, we have original matrix RSS first, plus multiplication of matrix delta with RSS complex conjugate and with matrix delta Hermitian. Then from right side, we multiply it with A Hermitian. And the last thing here, plus our noise. So we can see for both forward and backward parts, we have the same noise variance times identity matrix, and if we sum it up and divide it by 2, we'll have the same noise. So we have only one change here inside of spatial correlation matrix for sources. I will put this equation into the box, but first I will indicate that we call this overall matrix as RSS superscript FB. So next I put this equation into the box. In comparison with previous equations, for this resulting equation, I will give only underline with yellow color because I will highlight with yellow this part overall. So, of course, this equation is important for us. But here, more important to show this part with yellow. And next I will continue from this equation, why this part is important for us in this case. And then we will continue our forward, backward averaging things here.
Кошмарит там людей. Ничего нет. Потому что есть все не очень качественно. Я честно скажу, уже такие писали,
но поначалу, наверное, да, он будет скачать. начали ебать его, короче, за это времени. Да, там и сомнительно организует, который я разъебал. Блядь, сорвался. Блядь. Какую шау, говно, как таит, как помню. Ну да, да. Разработчики на Android как раз там лучше в России. А мы видим, блядь. Он удалился из сети, удалился в телеграм-аккаунт. У него была связь с командой, блядь, вот, мы просили его переработать как раз систему навигации. Он говорит, все, сделать, или там Xiaomi, очень ноунеймовые телефоны, на них будет не очень смотреться. Остальные смотрятся нормально. Говорит, ну, если включить кнопку навигации и делать ее цвет с панели навигации, вот здесь новый юзер будет. Ужасно. Человек. А если его под цвет различается, то ну, типа вот. Нет, мы даем его за это, потому что он черный. Перекрашиваю все. У тебя вообще навигация не спят. Ну, еще типа.
So, I think we can continue from this part. So, why I highlight only this part? Because I want to show you the connection between this forward special correlation matrix and what we have if we average over forward and backward special correlation matrices. So you can see the structure is the same. So A times RSS, but here we call it as RSS with forward backward averaging, then A Hermitian and plus noise. And then let's see two different cases. So first one, if we assume non-coherent or uncorrelated wavefronts, and if we assume coherent wavefronts or correlated. In this case, we'll have two different values for RSS. So here is RSS superscript FB. First, let's assume that we have uncorrelated signals. In this case, this RSS of B will be equal to the same RSS. RSS if the signals are uncorrelated. If the signals are uncorrelated, then this RSS and RSS of B is no. Let's write only RSS here. If the signals are uncorrelated, RSS is diagonal. And then if we look to RxX, forward, backward, this also is equal to RxX. Because if we put here RSS, we'll have the same first equation, which is forward special correlation matrix. And if we assume the case with coherent wavefronts, then our wavefronts will be decorrelated using forward-backward averaging. Otherwise, the wavefronts are decorrelated. The wavefronts are decorrelated. And let's go to one example, how we can represent our measurement metrics for forward-backward averaging case. So first we show why we use this forward-backward to decorrelate, and now how we can do it. What we need to use.
Извиняюсь, я с ключами ушел.
Хорошо? 421.
Нужно будет закрыть что-нибудь.
Нет, 421.
Да.
Хорошо. Example. Here we assume that the number of sources is equal to 2. So, example, number of sources, small d, is equal to 2. Then, let's say, if we calculate the expected value of absolute value of s sub I of t squared. So this thing is the variance of our sources. And let's say that this one is equal to sigma s squared. S for noise, but with subscript s for signal. And here, I is equal to 1 and 2, because the number of sources is 2. Then let's show that for signal vector we have S of t with two elements, S1 of t and S2 of t. And last but not least, we need to show the correlation between these two sources. For this one, we use special correlation matrix for signal, RSS. So here, first, we need to show that we have the variance equal to sigma s squared. And next, we need to show the correlation matrix. If these signals are uncorrelated, we will have only ones here on the main diagonal, and on the second diagonal we will have zeros for uncorrelated case. But we assume correlated case, so here we will have some correlation value rho 1, 2, and let's say that the same rho 1, 2 here, but with complex conjugate. And in this case, when we say that we want to decorrelate, we mean that we want to reduce these two sizes. So we want to equal these two correlation coefficients equal to 0 in ideal case, or close to 0 in, of course, non-ideal real cases. So let's write decorrelation means reduce the absolute value of correlation coefficient. So absolute value of rho 1, 2. Then we can show the measurement matrix in the following way. So as we showed before, matrix X is equal to matrix A times matrix of signal plus matrix of noise equal to n. And now for forward-backward averaging, we can call this X as X superscript F, so forward part. I will put this equation into the box, and then I will show you what we have for backward array. For the backward array, we will use X superscript B, which is equal to exchange matrix P of size M times complex conjugate of our original measurement matrix X. X with complex conjugate. Then let's put inside of this X complex conjugate these matrices A, S, and N, we will have first exchange matrix times complex conjugate of A times complex conjugate of S plus complex conjugate of N. And you can see the multiplication of exchange matrix with complex conjugate of array steering matrix is equal to original array steering matrix times delta. Of course, the main thing here, we multiply both the signal part and the noise part with exchange matrix. So this one also is multiplied with exchange matrix. So exchange matrix times complex conjugate of N. And then to estimate our forward-backward averaged special correlation matrix, we will define new measurement matrix. So to estimate, matrix RXX FB, we define matrix Z which is equal to concatenation of original matrix X with here we multiply from the left side with exchange matrix of size M. Here we have X complex conjugate, and from right side we multiply it with exchange matrix of size N, number of snapshots. So from left side it is the number of antenna elements or array elements, and from right side it is the number of snapshots. And let's show the sizes of these matrices. The number of columns of X is equal to N. This one is the number of snapshots. And in the same way, we'll have here the number of columns equal to N, because we just change the order of rows and columns. And the number of columns here is equal to, the number of rows here is equal to M, so the number of array elements. And now let's write down this new matrix Z using matrices A, S, and N, and also using with this concatenation thing here. In this case, the signal part will be equal to matrix A multiplied with concatenation of matrix S, and here we have matrix delta, this one, multiplied with S complex conjugate. And also we need to show this exchange matrix from right side. P of size N so the number of columns for both parts is equal to N. and the number of columns is equal to D, which is the number of sources here. So this one is equal to D. And then let's show what we have for noises. Plus, so here, for this matrix, we concatenate N from original or from forward part. And from backward part, we have this exchange matrix of size M times complex conjugate of noise matrix. And of course, exchange matrix from right side. P of size N. Here, the number of rows is equal to N is equal to N, but the number of columns is equal to capital M. Based on this information, we can write the sizes of this matrix Z. And of course, now we see what we have as the structure of this matrix Z. So this matrix Z is, of course, here we need to show that this one is matrix. Z is complex of size M times 2n. So we virtually double the number of time snapshots. And for this matrix Z, what we have? These matrices have the same structure as matrix X, the same structure as matrix X, which is equal to A times S plus N. So you can see we have A, then the part with signals, S, and the part with noise. But if we compare original matrix X and our new matrix Z, the number of snapshots, has been virtually doubled. Has been virtually doubled. And next, let's show interesting property of matrix Z first, and then we will go to argsex forward backward averaged. So let's note that what if we multiply complex conjugate of Z with exchange matrices from left side of size M and from right side of size 2n. So we have this exchange matrix times complex conjugate of Z times exchange matrix of size 2n. In this case, I will start with structure. So here we have maybe I will move this thing a little bit, and maybe I will do it like this one. So let's see. First, we multiply this part. So we will have exchange matrix times, of course, with complex conjugate, sorry. Here we have a complex conjugate. We will have something like this one. Yeah, okay. Then let's show the second part. So we multiply exchange matrix of size m with exchange matrix of size m. So it is just identity matrix. And here we have X complex conjugate and also complex conjugate. So let's show first with this double complex conjugate, and then we will reduce it to just X. And here we have an exchange matrix of size n. So first, let's show the sizes of this matrix: m, n, and n. And then for exchange matrix from right side, I will show it also with structure. So here we have 4 different parts. So first part, it is zero matrix. Then here, exchange matrix of size n. In this row, we also have exchange matrix of size n, and here zero matrix. So the number of columns and the number of rows and. Now you can see what we will have here. We multiply this concatenated matrix with concatenated row. So this one is equal to 0. This one is equal to X with double complex conjugate, so it is just X. Which is concatenated with this one, exchange matrix, complex conjugate of X times exchange matrix. So P of size m, complex conjugate of X times P of size n. And this one with zero matrix is zero matrix. And now what we have here, you can see that we have the same matrix Z. X, exchange matrix, X conjugate, exchange matrix. So this one is just Z. This type of matrices we will call as central Hermitian. matrix Z is central Hermitian. And I will give you slides for central Hermitian next. Then we will look to real valued subspace estimation. So next, we end with this note. Next, let's go to recall of estimation of RxX. So let's recall. With double line here. Estimation of special correlation matrix. Rxx with head is equal to the averaging of x times x Hermitian. So averaging thing is 1 over n, number of snapshots. Here we have x times x Hermitian. Or in another way, we can write down 1 over n. And here we can use the sum of multiplication of measurement vectors x for time t sub n with the Hermitian one. So x of t sub n Hermitian, where this small n goes from 1 up to capital N, overall number of snapshots. And now let's use the same thing, but for estimation of RxX forward backward averaging. So estimate of RxX FB. Let's use the same with RxX subscript FB with head as the estimation. Now, you should remember that when we use forward backward, we double, virtually double the number of snapshots. So we average over n 2 times n instead of n. So here we have 1 over 2 times n matrix Z times matrix Z Hermitian. And let's show the multiplication of these matrices with the structure of these matrices first. So what we have? 1 over 2n, and here Z is concatenation of x, then exchange matrix of size m, then measurement vector composite conjugate, exchange matrix of size n, and all these things, but with composite conjugate sign and transpose. So here we have concatenation of rows or columns, I think. X Hermitian. So Hermitian of exchange matrices is, or are exchange matrices. And here first I will show with two operations. So X complex conjugate and Hermitian times exchange matrix of size n. N. Oh, wait. Yes, of course, we calculate the Hermitian one. So first here n, and here m, of course. So let's multiply these two matrices, and we will have 1/2n. First here x times x Hermitian plus exchange matrix of size m times x complex conjugate times x complex conjugate Hermitian times exchange matrix of size m. Or we can write here, so this one is Rxx we've had, and this one is Rxx we've had, but with complex conjugate. And of course, in this case, we need to move 1/n inside of these two correlation matrices. We'll have 1/2. Here we have Rxx we've had plus exchange matrix of size m, then Rxx we've had complex conjugate and exchange matrix of size m. So the next step is to find the signal subspace. Signal subspace estimate. Signal subspace estimate could be obtained by calculating we have two options here as before. Option A, we can calculate the singular value decomposition of Z, the singular value decomposition of matrix Z, our new measurement matrix, which is of size complex of size m times 2n. Or we have second option, option B. We can calculate the eigenvalue decomposition, EVD, of Z times Z Hermitian. Which is in this case also complex, but of size m times m. So So it is square matrix. So we use one of these options. 503. We use one of these options to estimate signal subspace. This one give us an information about U sub small s. Here I will use small s, which is complex of size m times small d. And next, we will use real valued subspace estimation here. In the following way. So let me write down. S and okay. So let's write here 4.5 subsection 4.5 real valued subspace estimation. Real valued subspace estimation. Red color for 4.5. And 3 underlines for the name. Real valued subspace estimation. Here first we start with definition. We'll have 2 definitions, and then for this part we will have 1 slide. Definition. So underlines. Definition A. So first one. Matrix M of which is complex of size P times Q. Complex of size P times Q is central Hermitian. Is central Hermitian. If when we multiply this matrix M complex conjugate with two exchange matrices from left side and right side. So exchange matrix P of size P times complex conjugate of M times exchange matrix of Q. So this matrix M is central Hermitian if this multiplication is equal to the original matrix M. This one for central Hermitian matrices. And then let's show one more time what we mean when we say left bi-real. So definition B here. Let's assume matrix Q, which is complex of size P times Q as matrix M. And we will call this matrix Q as left bi-real. So this one is left bi-real if when we multiply the complex conjugate of Q with exchange matrix from left side, so exchange matrix of size P times complex conjugate of Q, this multiplication is equal to the original matrix Q. This one for left bi-real. Or of course, we can show it vice versa. On this equation, we can say that complex conjugate of Q is equal to the multiplication of exchange matrix with original matrix Q. So next, we will use these two definitions. So I will put here number 1 for this equation and number 2 for this equation. And also I will put these two definitions into the box. And I will separate it with horizontal line. So into the box here. And let's separate it. So now we have two definitions for center Hermitian and for left bi-real, respectively. Now let's write down an example with 2 points here. Example. We assume, or I will give you the definition of sparse left bi-real unitary matrix of size, in this case, Q times Q. So I will introduce you sparse left bi-real unitary matrix of size q times q. And before we start, we have slide number 21. Slide 21. So let me show you this slide. I think we have something like definition here. So in this case, you can see that we want to get from central Hermitian matrix real matrix. First, we show a complex matrix M is called central Hermitian. If this equation works, and same one for matrix Q, we call as left by real. And here you can see two different sparse left by real matrices. So first one, when this Q, the number of rows and columns, is even, and the second one, when the number of rows and columns is odd. Внутри оставил? Хорошо. Спасибо, тебе тоже. So, boom, boom, boom. First, let's show. Oh, I think we can start with even and odd, and then I will add you one interesting property of these sparse left by real matrices. So let's start with even, when Q is even. Point number one, Q is even. Or we can show it in the following way, that Q is equal to 2 times n.
Ильдар Айдарович, мы не видим.
Вот попался я снова. Забыл. Вот. Q is even, or we can show it as Q equal to 2 times n, where n is equal to 1, 2, 4, 1, 2, 3, 4, 5, and etc. And here for this example, e.g., we use Q equal to 4, or n in this case equal to 2. Let me move my page. Here we will use, for this sparse left by real matrix, Q. So we write Q. Then in subscript, we show that the size of this matrix, so 4. And in the, let me check. Yeah, for this one, we can show that, let's add in superscript S, which means our matrix is sparse. This one is equal 1 over square root of 2. And here next we have matrix of the following structure. here we will have concatenation of 4 matrices of size 2 by 2. First matrix is identity matrix. 1, 0, 0, 1. Then second matrix also identity matrix, but this one is multiplied with j. So we have here j 0, 0, j. Then third matrix is exchange matrix. So we have 0, 1, 1, 0. And here the last one is also exchange matrix, but we multiply it with minus j. So here we have 0 minus j and minus j 0. So this type of a matrix is sparse left by real unitary matrix. And here it is even. And let's show what if the number of rows and columns is odd. Number 2, Q is odd. In this case, we can write Q is equal to 2n plus 1 to get odd Q. Let's use the same number for n. So it is 2. In this case, Q will be equal to 5 and equal to 2. As for even matrix, we use Q. In subscript, we show the size of this matrix, and in superscript, we show that this matrix is sparse. So here we have the same 1 over square root of 2. And here we have the same structure, so the same 4 matrices, but we need to add 1 row between them and 1 column between them. So we will have something like, maybe let's write down all values, and then I will show the parts of these matrices and our additional row and column. So here we will have 1, 0 as before, and then additional 0 here, and 0, 1. Then second column, 0, 1, additional 0, 1, 0. Then we need to add this additional column, which is double 0 here, then square root of 2, and double 0. And in the same way for column number 4 in this case, and column number 5. So it is third column, j 0, 0, 0 minus j, and 0 j 0 minus j 0. So here we have concatenation like this one, like this one. And you can see from these 4 angles we have the same matrices, but we need to add this additional row and additional column. Then what else we can add here? The property which is, oops, sorry. If we multiply Q of size, for example, Q, yes, and this one is sparse. So we take the Hermitian of this matrix and multiply by itself. Hermitian multiply by itself. We will have an identity matrix of size Q, because this matrix is unitary, as we say before. And let me, okay, maybe I will change this one. So here you can see that complex conjugate of M showed with this, or is shown with this top line. So let's maybe add that here in the slides 21, that this M with top line is equivalent to the M with complex conjugate, like this. Or maybe I will try to change this slide, maybe. Boom, boom. And now we can go next to, maybe I will start. Let's check. We have 30 minutes. Let's write down one sentence here. Any matrix. So remove this page. Any matrix Q, which is equal to the multiplication of this sparse left by real unitary matrix times matrix E so any matrix Q, which is equal to Q, which is equal to multiplication of Q sub Q times E with this matrix Q sub Q left by real and matrix E real of size Q times P this overall matrix Q is also left by real, is left by real. I will put this equation into a block box and overall sentence into a box. So what we have from this sentence, if we have some real matrix and we multiply it with, from left side, with left by real matrix, this new matrix will be also left by real. And let's see that this sentence is correct. So let's multiply this Q. Of course, we take the composite conjugate of it and multiply with exchange matrix from left side. This one of size Q times Q composite conjugate. So here we have exchange matrix times sparse matrix composite conjugate times original matrix E and. So we say that this matrix Q sub Q is left by real. In this case, if we multiply it like this one, we will have the same matrix Q from this definition. So exchange matrix times Q composite conjugate is equal to Q. And here we have exchange matrix times Q composite conjugate is equal to original matrix Q sub Q. Multiplied with E. And you can see that this one is equal to original Q. So which means we get everything right. Next, we have an extension for slide 21, slide 22. Slide number 22. Here in this slide, if I'm not mistaken, we have one theorem, yes. So we have two matrices, Q sub pi and Q sub Q, which denote arbitrary non-singular left pi real matrices, or this sparse left pi real unitary matrix, we can call it. And first one of size Q times Q, and this P times P, and the second one Q times Q, respectively. Then we have this bijective mapping, you can see. And let's prove this theorem. And this one we will use next to get central Hermitian matrix mapped onto real space. So we'll have from central Hermitian matrix real matrix. So let's prove. For this proof, we have 6 lines. So proof.
Ильдар Айдарович.
Я все забыла. Вот первую лекцию я не забывал странным образом. Вторую и третью лекцию я всегда забываю.
Уже
Мы просто устали.
Возможно. So, proof. Let's add here theorem from slide 22. First, we use first equation from this definition of central Hermitian. We use first equation, but here we represent this equation with respect to M complex conjugate. M complex conjugate is equal to exchange matrix of size P times original matrix M times exchange matrix of size Q. This one we will use next, so I will indicate it with number 3 here for this. Then we use second equation from our definition. So for this left by real. Number 2. And what we have here. First, let's show this matrix Q sub pi, which is equal to exchange matrix of size pi, or let's say P of size P, times complex conjugate of this sparse matrix, or if we calculate the inverse of this matrix, we will get complex conjugate of this matrix inverse, and then we multiply from right side with exchange matrix of size P. This one, equation number 4, we will use it next also. And let's, in the following way, show this equation for matrix Q sub Q. So matrix Q sub Q is the exchange matrix of size Q times complex conjugate of this matrix. And this one, number 5. And now we use this, let me check, mapping matrix. Mapping matrix, yes, bijective mapping phi. Ah, and of course, we need to change here. We say that this phi of matrix M is equal to Q sub P inverse times M times Q sub Q. So this is our bijective mapping. And let's see what we have if we calculate the complex conjugate of this phi of M. Phi of M with complex conjugate sign. In this case, we need to take the complex conjugate of all these matrices. Here we'll have Q sub pi complex conjugate inverse, then matrix M complex conjugate, and Q sub Q complex conjugate. Then let's use our third equation here. So next we use equation number 3. And instead of M complex conjugate, we use this right side of the third equation. We have Q sub P complex conjugate inverse multiplied with exchange matrix of size P, then matrix M, then exchange matrix of size Q, and sparse matrix of size Q complex conjugate. So this one from our this one from our equation 3, it is equal to M complex conjugate. And now we use equations 4 and 5. Let's see that this one is the same to inverse of Q sub pi. So it is from number 4. And this part from equation number 5. So it is equal to Q of size Q. Which means we have inverse of matrix Q sub pi times M times Q sub Q. And you can see that it is the same bijective mapping phi of M. So it is phi of M. QED. So why we do these proof things? This bijective mapping Q of M, phi of M, and here phi of M, it is the mapping of matrix M into real plane, let's say into real plane. In this case, this phi of M have the same sizes as matrix M, but this one is real, but this one, original matrix M, is complex. And from this proof, you can see we have original phi of M, and we try to calculate phi of M complex conjugate. If we have that this phi of M is complex, we will have something complex things here with complex conjugate things. But you can see when we calculate the complex conjugate, we have the same value, phi of M. In this case, we know that this phi of M is real. And now how we can use this theorem, or how we can use this bijective mapping. Let's write application. Application to underlines. So I think we can write down the application field. Maybe, okay. Let's see. So here we introduce sparse left by real unitary matrix Q of size M. Q of size M, and this one is unitary. unitary, and of course sparse and left variable. What we have for this unitary thing? If we calculate the Hermitian of this matrix, we will have an inverse of this matrix, or vice versa. If we calculate inverse, we can change it with Hermitian sign. Then let's write down our matrix Z, which is equal to the concatenation of X and here we have matrix P of size M times X complex conjugate times P of size N this matrix is complex of size M times 2n. And this matrix is central Hermitian. Is central Hermitian. And for central Hermitian matrix, we can calculate this bijective mapping. So from complex plane into the real plane. In this case, we use phi of matrix Z, which is equal to this unitary matrix QM Hermitian. Yes. Why Hermitian? Because we can change the inverse sign to the Hermitian sign times our matrix Z times Q of size 2n. And let's show what we have just inside of this matrix and how we denote this bijective mapping. So here we have Q of size M Hermitian. Inside of Z we have X concatenated with P of size M times X complex conjugate P of size N, and from right side Q of size 2n. And we denote this bijective mapping of Z as this calligraphic T. Of matrix X, which is real, of size M times 2n. So we have two options. First one, we can show bijective mapping of Z, which is real, or we can show it with transformation of X, which is also will be real. So for this one, we have slide number 23. Slide 23. Let me switch to the slides. So this, let's say we have summary for forward-backward averaging or something like this one here. This one is applicable to central symmetric array configuration, which means we have the centroid in our antenna array. Let's see. Then this forward-backward averaging or this pre-processing step efficiently doubles the number of available observations. So it is virtual double thing. So we do not collect new information. We work only with our received or measurement metrics. This one decorrelates two highly correlated wavefronts if we assume number of wavefronts equal to 2. And it works without this sacrificing of aperture. In this case, we need to create this type of a matrix Z. You can see the structure here, and of course, this X with top line here is X complex conjugate. Then Z is central emission, and we can use from one side transformation of X. In this case, of course, we will use bijective mapping of Z, which is shown as this one. And you can see we go from complex values of Z to the real values. And next, we calculate. Of course, we have two options as before. We can calculate real valued singular value decomposition of this transformation of X, or we can calculate eigenvalue decomposition of Tx times T Hermitian of X. And then we find, yes, here we have, let's say, signal subspace equal to E of S, E sub S, and then we find D dominant left singular vectors of Z in the following way. What else here? 24. Okay, we have here example with this slide. Let's write down it. And then maybe I will leave corollary for the next lecture. Or maybe we can try to end all these parts right now. Okay, let's try to end all these parts right now. And then next lecture, we will start with new subsection called as 1D unity aspect. So let's try to end this part. So here we have an example. For slide 24.
Ильдар Айдарович,
А,
надо отдыхать уже просто.
давайте закончим быстренько. Быстро пробежимся. Потому что в таком случае нам не придется дописывать и возвращаться обратно к этой теме, так скажем. Example, slide 24. Slide 24. here we have only one corollary, two additional things from this summarization, and what if we use FBA. So that's all for what we need to do for today. So in these slides, we have QM equivalent to QM superscript S and Q2N equal to Q2N superscript S. So let's leave this example for next lecture. So we will start with summarization. I will show you this example next lecture, and then we'll go to the next subsection. But now we need to end with corollary. Corollary let matrix M complex of size P times Q let this matrix be central Hermitian. Central Hermitian. And assume that the singular value decomposition, that the SVD of the real valued matrix of the real valued matrix here we indicate SVD with blue color. So we have SVD of real valued matrix phi of M. So this bijective mapping, which is equal to Q sub P Hermitian times our central Hermitian matrix times Q sub Q. And this singular value decomposition of this matrix is given by also blue color for this real valued matrix is given by phi of M equal to unitary matrix. Here we show it with subscript R times matrix sigma times matrix V sub R Hermitian. Blue color for this one. And of course, for all these sentence where our Q sub pi and Q sub Q, Q sub pi and Q sub Q are unitary, and left pi real, and left pi real. Then we can show that singular value decomposition of matrix M, then and singular value decomposition of matrix M is obtained as so SVD of M is equal to M, or denoted as M, and equal to, here we have Q sub pi times U sub R times sigma times V sub R Hermitian, which is multiplied with Q sub Q Hermitian. I will show these two parts with brackets, and also I will add yellow color here. This matrix is complex of size P times Q. Let's put this overall corollary into the box. Yep. This one and like this one. So from this corollary, let's show the main idea. We compute a real valued SVD, compute a real valued SVD of matrix phi of M to obtain the complex valued SVD of M. The complex valued SVD of M. And this thing, all we do to reduce complexity, computational complexity. Reduce computational complexity. So how it works? When we use forward-backward averaging, we double the number of snapshots. But in this case, let's assume that our N is large, and we also double this value. We have larger matrix overall, matrix Z. In this case, we will have complex computations for singular value decomposition of this overall matrix Z. And to reduce this computational complexity, we first go to the real values using with bijective mapping. When we calculate singular value decomposition, and then we go back to complex value singular value decomposition of original matrix Z. And two last points here. If forward backward averaging is used, if FBI is used, we calculate singular value decomposition of Z which is complex of size m times 2n, or we can calculate EVD of Z times Z Hermitian, which is also complex but of size m times m. And these 2 points, SVD or EVD, can be obtained by calculating the, so first point, SVD of the transformation of X, which is equal to bijective, which is equal to bijective mapping of Z, which is real of size m times 2n, or we can calculate EVD or EVD of this transformation of X multiplied with Hermitian of this transformation, which is also real of size m times m, and of course, respectively. If we calculate SVD, we use SVD. If we calculate EVD, we calculate EVD. So that's all for today. We did a great job today. Really, really big things here. But that's all good for us because we can start our next lecture with new subsection. Here we'll have another type of Aasp called as unity Aasp. So, thanks for today's work, and have a nice evening.